Good morning or good afternoon, and in this video we will be talking about acids and our bases in the context of organic chemistry. So what are acids and bases? Acids and bases are actually defined differently depending on two primary theories. We have our Bronsted-Lowry theory and we have our Lewis theory. We will be talking about Bronsted-Lowry theory first. And in Bronsted-Lowry theory, it states that an acid is a substance that donates a proton, while a base is a substance that accepts a proton. Please take note that the proton is synonymous with the hydrogen ion, H positive, because the loss of the valence electron from a neutral hydrogen element leaves only the hydrogen nucleus, which is remaining a proton. So remember that our neutral hydrogen has one electron and one proton. Now, if the electron leaves, what you will have is only one proton left. And since it has no more electrons, hydrogen ion effectively is a proton because there's nothing left in the atom, only a proton. So this is the general different parts of our Bronsted-Lowry theory. We have the acid, the base, the conjugate acid, and the conjugate base. So let's define our conjugate acid and our conjugate base. So a conjugate acid is simply a base that has received the proton, and the conjugate base is an acid that lost the proton. Okay, so in our naming sense, please take note that H represents our proton, A is our acid, and B is our base. Now, it could be acid or it could be base or it could represent any compound. However, what you need to focus on is on the letter H. Where did the letter H come from and where did the letter H go to? Okay, so we have an acid and a base. So in a general sense, an acid is a substance that donates a proton, while a base is a substance that accepts a proton. Okay, so in a general sense, we have our acid, we have our base. The proton is represented by the letter H right here. So in this reaction, as you can see, the acid will donate a hydrogen at proton towards the base. So it will go towards the base and the base accepts the proton. Okay, so what is in the second half of our reaction is our conjugate acid and our conjugate base. So the acid becomes a conjugate base since it lost the electron, and a base became the conjugate acid because it gained the proton. So an acid becomes a base and the base becomes an acid because the base has the proton now. Okay, so another example is is on the bottom. So this is an acid. It has the hydrogen atom here. It will donate the hydrogen atom towards this hydroxide ion right here, and it will form. So this hydroxide ion will form our water, and this one will become our acetate. So this is our acid, this is our base. Our acid becomes our conjugate base, and our base becomes our conjugate acid. So please clarify the four terms. We have our acid, we have our base, we have our conjugate acid, and we have our conjugate base. Okay, so this is just another example. We have water and we have NH3. It forms hydroxide and our conjugate acid. And NH4. Okay, so water gives a hydrogen ion towards our ammonia, and water becomes hydroxide. Ammonia becomes ammonium ion, and it carries our NH4. Our ammonia received our proton. Okay, as you can see from the two reactions, they both used hydroxide, and they yield water and water and hydroxide. Okay, we have this uniqueness of water in a sense that water can act as either an acid or a base. Okay, when water acts as an acid, what happens is water will become hydroxide, and you have a loose proton, since an acid donates a proton. So water loses a proton, particularly hydrogen, and what you will have is hydroxide and hydrogen ion, or our proton. If you want it to act as a base, so water acting as a base, it will receive a hydrogen ion. What will happen is you will form our hydronium ion. Hydronium ion is net positive in nature. Okay, so again, water giving off a hydrogen atom acts as an acid. Water that receives a hydrogen ion, which becomes hydronium, acts as a base. Next, let's talk about the acid and base strength. So the exact strength of an acid, or HA, is in aqueous solution is described as KEQ for the acid-base equilibrium. So this is the general formula for getting our so this is the dissociation formula of our acid. So acid combines with water, the acid will lose the proton, and the proton will be attached to water, and water will form our hydronium ion. Then the acid will be left alone and will become our conjugate base. Now, for getting the equilibrium constant, this is the particular formula of that chemical reaction, or our dissociation reaction of acid in water. So KEQ equals concentration of hydronium ion multiplied by concentration of our conjugate base over our acid multiplied by the concentration of water. So these are all in the concentrations of molarity. Okay. However, they are usually very small or very minute. It can range from 0.00, 0.3 or less. Okay. However, this is not the final formula for our acid strength. Since it is in aqueous solution. So in the dilute aqueous solution normally used for measuring acidity, the concentration of water remains constant at approximately 55.4 molar. So therefore, we can actually exclude this from our expression, and we can now create a new constant, particularly our acidity constant, Ka. The acidity constant for any acid HA is simply the equilibrium constant for the acid dissociation multiplied by the molar concentration of pure water. So simply put, we have our new KEQ, or our the acidity constant Ka equals our KEQ multiplied by water, or simply our concentration of hydronium ion multiplied by our conjugate acid over our acid. So we can actually exclude water from our equation. Okay. So how is this useful? So Ka signifies the strength of our acid. The larger the Ka of our acid, the stronger it is, because our Ka describes how much proton it can give. Okay. The higher the Ka, the more protons you can give. The more protons you can give, the stronger your acid is. So large Kas equals stronger acids, and smaller Kas equals our weaker acids. Now, since Ka will still be very small, it's an unwieldy unit to be held, we have changed it into our pKa. So we do not usually see Ka in normal practice. What we see is our pKa. So for convenience, acid strengths are usually expressed in pKa values instead of simply Ka values. To get our pKa value, we simply need to get the negative log of Ka. Okay, so you get the negative log of your acidity constant. However, this in turn will reverse the relationship between the strength of an acid. If you have a strong acid, you have a small pKa. If you have a weak acid, you have a large pKa. Okay? So baliktad po. A strong acid has a small pKa, and a weak acid has a large pKa. So in this slide, next slide, we have the relative strengths of some common acids and their conjugate bases. So as you can see, the strongest acid here is our hydrochloric acid, which has a pKa of negative 0.7. Negative 7.0. Remember, the smaller our pKa is, the stronger our acid is. And the larger the pKa is in terms of our ethanol, ethanol can give off some hydrogen proton. So it can act as an acid also. It has a very weak acidity, and hence it has a large pKa of 16. Okay? Water has a pKa of 15.74. So although water is relatively neutral, when acting as an acid, the pKa is 15.74. Okay, remember our number line. As you go to the left, the stronger the acid is. As you go to the right, the weaker it is. 0, negative values, positive values. So this is when describing our acid strength. Please take note in the table that there is an inverse relationship between the acid strength of an acid and the base strength of its conjugate base, meaning a strong acid has a weak conjugate base and a weak acid has a strong conjugate base. Next, we have predicting our acid-base reaction. So these are a set of rules or a set of guidelines when you have 2 or more acids in a solution. Remember, class, when we have an aqueous solution, water can act as an acid and can act as a base at the same time. So most of the time, when predicting acid-base reaction, you just need to know if water will act as a base or water will act as an acid. So you need the knowledge of pKa for this one. So to start, hydrogen ion will always go from the stronger acid to the stronger base. Next, an acid will donate to the conjugate base of a weaker acid, and a conjugate base will remove the proton from a stronger acid. The product conjugate acid in an acid-base reaction must be weaker and less reactive than the starting acids, and product conjugate base must be weaker and less reactive. So basically, when you react two substances together, it will not react. It will react, but the products will always be weaker than what you started with. Okay, so let's have an example here on the screen. So number one, the hydrogen proton will always go from the stronger acid to the stronger base. Okay, so we have the stronger acid and the stronger base on the left side of our reaction. Okay, what will happen is acetic acid here will give to a stronger base, which is our hydroxide. It will not give the hydrogen towards the weaker base, which is our acetate ion. So this will not occur. Okay, next is, let's remove the writing. An acid will donate to the conjugate base of a weaker acid. Okay, so the weaker acid here, in this case, since if water acts as an acid, it will become hydroxide. Okay, so this is actually the acid and this is the conjugate base of our water. So in this case, an acid will donate to the conjugate base of a weaker acid. Since this is the conjugate base, again, the hydrogen from acetate will give it to the conjugate base of the weaker acid. So these two are generally the same, but they state it differently. So move to writing. Next, a conjugate base will remove the proton from a stronger acid. So again, this is our conjugate base and this is our acid. Also acid. This is stronger. This is weaker. So what will happen is water, when acting as a base, will not give to its conjugate base, since the conjugate base will get the hydrogen from a stronger acid. Okay, and lastly, the product conjugate acid in an acid-base reaction must be weaker and less reactive than the starting acid, and the product conjugate base must be weaker and less reactive than the starting base. So reactivity is not shown in this reaction. Next, we have our organic acids. So these are characterized by the presence of positively polarized hydrogen bonds. We have two types of our organic acids. These are fairly similar in structure to one another. That is why they can easily be distinguished from other compounds. So the first type of our organic acid is a compound which has a hydrogen bonded together with oxygen, particularly to an electronegative oxygen. So these are your alcohols, which contain our hydroxide group, also our acetic acid, which is a carboxylic acid. Again, there is still an OH in that structure. Also, another type of organic acid is those that contain a hydrogen atom bonded to a carbon atom next to a carbonyl group, or our C double bond O, such as our acetone. So acetone looks like this. There's a carbonyl group, there's a carbon here, and which has hydrogens bonded to it. Okay, so in this description, hydrogen atom bonded to a carbon next to a carbonyl group. So this fits the description of our organic acid. So here are some examples of our organic acids. So we have methanol, an alcohol, acetic acid, and we have our acetone. So the acidity is due to the fact that the conjugate base resulting from the loss of hydrogen is stabilized by having its negative charge on a strongly negative oxygen atom. The conjugate base is also stabilized by resonance in acetone. So take for example this one right here. So this is our methanol. If hydrogen leaves, aalis si hydrogen, what would remain is a electron pair. And that electron pair will remain on the electronegative oxygen atom. And this structure is stabilized because the negative charge is on the electronegative element. So that is why it can act as an acid. On the case of acetone, if acetone loses the hydrogen atom on the OH group again, what would happen is, look at the structure here. It can resonate to form two resonance structures, okay, either one or two, and as we alluded to earlier in our resonance, a structure which has more resonance forms are more stable. So acetone can behave like an acid because it can stay stable due to resonance. Okay. So this is simply showing what will happen if acetone loses our hydrogen group, or our hydrogen atom. So we have our carboxylic acids. So our compounds called carboxylic acids, these contain our carbonyl group. Okay. C or COOH if you want to see it that way. And they occur abundantly in all living things and are involved in almost all metabolic pathways. You will encounter them later in your biochemistry. So you have your acetic acid, pyruvic acid, and citric acid. These are all organic acids. Organic bases, on the other hand, are characterized by an atom with a lone pair of electrons that can bind to hydrogen. Usually this is nitrogen. Okay, nitrogen has a lone pair kasi. Oxygen-containing compounds can also act as bases if there is a sufficiently strong acid, and ethanol and acetone, for instance, act as acids when they donate a proton, but they act as bases when their oxygen atom accepts a proton. So it could be either a nitrogen-containing compound, or an alcohol, or an acetone, a ketone, if there is a presence of a strong acid. So for Lewis acids and the curved arrow formalism, the fact that Lewis acid must be able to accept an electron pair means that it must have either a vacant low energy orbital or a polar bond to hydrogen, so that it can donate hydrogen ion, which has an empty 1s orbital. For example, various metal cations such as magnesium cation are Lewis acids because they accept a pair of electrons when they form a bond to a base. So take for example our next slide, a Lewis acid and a Lewis base here. So this is a organodiphosphate ion. As you can see, there are electron pairs that are available to bond with our or to be shared with our magnesium. Since magnesium has a vacant 1s orbital, since magnesium is 12, 1s2, 2s2, 2p6, 3s2, so 10, 12. This is magnesium element. Magnesium ion has an empty 3s2 orbital. Okay, so it can bond twice, or it can share an electron. They can share an electron pair twice. Okay, so what will happen is magnesium, which has a empty s orbital, can bond with our oxygen here because of their lone electron pairs. Can form an acid-base complex. So these are other examples from Lewis bases. So similarly, many transition metal compounds such as titanium chloride, ferric chloride, zinc chloride, and tin chloride are Lewis acids. Okay, they can bond with oxygen. So these are some Lewis acids. As you can notice, what is the difference between Lewis acids and our Bronsted-Lowry acids is we have a much larger pool of Lewis acids as to compared to our Bronsted-Lowry definition of our acids. Lewis bases, on the other hand, is a Lewis definition of a base as a compound with a pair of non-bonding electrons that it can use to bond to a Lewis acid. The most common is either oxygen or nitrogen containing compounds since they have lone pairs of electrons. So ang hahanapin niyo po is either oxygen or a nitrogen. These are some examples of some Lewis bases. Notice that in the Lewis bases just given, some compounds such as carboxylic acids, esters, and amides have more than one atom with a lone pair of electrons. Okay, you can see na dalawa ang kanilang oxygen. Okay, so how will this pose a problem? It doesn't actually pose a problem, but in theory, these compounds have two binding points since they have our lone pairs of electrons. Therefore they can react at more than one site. However, reaction normally occurs only once, and the more stable of the two possible protonation products is formed. For example, in our acetic acid, okay, so this is our acetic acid. It can either bond here or here. Okay. If it reacts with sulfuric acid, it only acts on the doubly bonded oxygen because the product is stabilized by two resonance forms. So it will act on this oxygen here, not here. Let's see the structures. Okay, so this is acetic acid. Okay, I just redrawn with sulfuric acid. So if it acts here, okay, so on this oxygen, dito magkakabit ng hydrogen. Okay, simply put, the double bond can break to form hydroxide. on top. And there could be a resonance form from a lone pair electron from our hydroxide substituent. This can move. Okay. However, if sulfuric acid acted here, okay, for example only, if sulfuric acid acted on the hydroxide bond, so dun siya magkakabit ng hydrogen, you will not form any resonance form. Okay, your oxygen already has 3 bonds, and this cannot move here. Since it will become 4 bonds for oxygen. So this is unstable. This is not formed. So this will be the only resonance forms that will be present in the succeeding reaction. Okay, that would be all. Thank you for listening. You can refer to our book and to also our Moodle for more information on the topic. Thank you and have a pleasant day.